So this video is going to discuss interaction or effect modification, and these are basically the same terms, just used in different contexts. Interaction is usually more statistical, effect modification is usually more of an epidemiology term, and this is one of the more difficult concepts in epidemiology, so I'm going to do my best to explain it in a few different ways, so hopefully one of these demonstrations helps you out. So just a kind of broad definition, an interaction is when the relationship between an exposure and an outcome is different among the strata of another variable. So just to illustrate this, we have a situation here where on the y-axis we have cholesterol measured continuously. We have BMI on the x-axis, low and high, and we have this relationship stratified by smokers and non-smokers. So you can see here that although when you're a smoker, you have higher cholesterol regardless of your BMI. The relationship between BMI and cholesterol is the same regardless of whether you're a smoker or non-smoker. And what I mean by that is the slope is the same, and that's where we get our measure of effect, something like an odds ratio. And basically that means that the relationship between BMI and cholesterol is the same regardless of whether you're a smoker. This is a more complex situation where now they have different slopes. So you can see that if you're a smoker, um, the effect of having a high BMI is greater. It leads to a steeper slope. So the relationship between BMI and cholesterol is different among the smoking and non-smoking strata. This is just a model representing kind of what we were just talking about. So this outcome is concentration of cholesterol. You have your baseline risk and the effect of BMI, smoking, and their joint effects. So their interaction term, and both the notation and how you would input this into SAS are the same. It's just the two variables you want to create an interaction for with a star in between. And as far as how that interaction term gets created, it's as simple as just multiplying the data. This is an example where it's two categorical variables with one as being present and zero as it being absent. The actual interaction term would just be multiplying these two. So when any one of them is zero, there can't be an interaction. The only situation where there can be is when they're both there, so one and one. And a similar thing applies as if we were if we're using BMI as a continuous variable. Whenever smoking is absent, it just cancels, but whenever it's present, you're able to multiply it across. And where this number would fit in is basically here. We'd have our slope for the interaction effect, and it would go in here. And this is just an example of output. I'm not going to go into what it is. The main thing I wanted to draw attention to is just that we have this continuous variable, 4 levels of a categorical variable, and these 4 levels of the interaction between the two. And basically for this interaction term to be significant, it only needs one of these levels to be significant. And these are betas, not odds ratios, so we can see that there's at least one that doesn't cover 0, so we would call that interaction term significant. I wanted to break down the structure of these two lines, this one being the steeper relationship when you're a smoker between BMI and cholesterol, and this being the more shallow one when you're a non-smoker. So using the equation we came up with up here, if you're a non-smoker, let's start with the blue one. Wherever smoking shows up, we'd input a 0 there because you're a non-smoker, and that would cause both these terms to cancel because that would be multiplied by 0, and that would be multiplied by 0. So now we have everything we need to describe this line, the non-smoker line, where we have the intercept, where the line begins, and that's the kind of baseline risk that affects everyone, and then we have the influence of increasing BMI. I'm using the continuous version of BMI, where for every 1 unit increase in BMI, that would be multiplied by the slope, which permits the line to get a little bigger for every unit increase in BMI. And to talk about why this one has a different slope, let's plug in the numbers the same way we did before, where now we have this is the smoking group, so we'd put a 1 wherever smoking shows up. So that permits both the the B2 term and the B3 term to remain. And all I did in this step between this one and this one is just switch the place of these two variables to make the next step more clear. Because now we have beta 1 and beta 3. That's the BMI one and the interaction one. They both have BMI, so that lets us factor that out. So now we can describe the line where the intercept is the combined effects of the regular intercept and B2, which would just be multiplied by 1, so it doesn't have anything to increase it any further. So that's where the red line begins. And the reason its slope is steeper is because in addition to that B1 slope that caused this to go up. So like here, whenever BMI increases by 1, that is multiplying this B1 by a higher number. Now the same principle applies, but the slope is now B1 plus B3, so that's going to be a higher number. Or I guess if it's a negative interaction, a lower number, but just for the sake of this example, as long as it's just a number above, like that's above 0, basically it's going to cause the slope to be at least a little bit steeper. Because for each increase in 1 unit of BMI, it's multiplying it by a number that is larger than B1, which would be however much beta 3 is. When it's a binary outcome, so far I've been showing you like cholesterol as the concentration of cholesterol as the outcome. If it's binary, it's still the same things apply basically with logistic regression, where it would just be the log odds. So I also just wanted to illustrate how interaction is detected on an additive and multiplicative scale. So an additive scale is how linear regression takes place, where the increments of the y-axis they go up by an equal amount each time. And I just wanted to describe how if we had this table here where we have the rate of lung cancer depending on whether someone is exposed to asbestos or a smoker, we have obviously the lowest rate being when you're neither, and then higher when you're a smoker with no asbestos, and also above the baseline risk when you're exposed to asbestos but not a smoker. But what would we expect this joint effect to be if it's on an additive scale? Basically, it's the baseline risk plus excess risk, and this is kind of weird, and I'm just gonna give something that's gonna maybe make that a bit clearer. So this is basically the same relationship. Rate of lung cancer. We have smoking and non-smoking, but this group is asbestos positive and this group is asbestos negative. So you can see that the relationship between smoking and lung cancer is the same in the two groups. So like the risk difference is 3 minus 1 is 2, 5 minus 3 is 2. So the effect between smoking and lung cancer is not different in this scenario on the two strata of asbestos. It's tempting to think that like the combined risk of being both exposed to asbestos and a smoker would just be adding the two rates together. So adding like 3 plus 3, but that would come out to 6. And we can see here that in order for the risk differences to be the same, this would be 5. Where if it was 6, then that all of a sudden would have a risk difference of 3, and we would have an interaction. And yeah, what I'm saying when I say the expected rate, I mean what you'd expect if there's no interaction. But what you typically do is you use the excess rate. So by excess rate, I mean that's above this baseline rate. So this is someone who's both asbestos negative and smoking negative. So the general population, we have this increased risk from smoking, which is 2 units here. And we have this group where this is the joint effects group. We have asbestos positive non-smokers. So this is the isolated effect of asbestos. That's also 2 units above. So yeah, that's how we came up with these excess effects. So the expected joint effect in this case would be this baseline risk plus the excess of the excess from smoking and the excess from asbestos. So if you actually just kind of look at it, because there's no point in adding this each time, you just add the amount that smoking adds to this risk and the amount that asbestos adds to this risk. So basically, putting that on top and then putting that on top, you end up with 5, which is what we have here. So back to our example before, this is slightly different data. I probably should have just used the same data for both, but this is an example where when you are a smoker without asbestos, you have a rate of 3, and when you're exposed to asbestos, it's a rate of 2. We can just use this equation I showed before, where we have the baseline risk plus excess for smoking and excess for asbestos, and we can come out to an expected joint effect of 4. And if our if we find that, if we find a rate of 4 in those that are both smokers and exposed to asbestos, then we know that there's no interaction happening, and the interaction term isn't adding any value. If we were to see that it came out to above 4, 6 in this case, that would be an example of synergism, where the effect of smoking and asbestos together is greater than the sum of their individual effects. You can also see antagonism, where the effect of smoking and asbestos together is less than the sum of their parts. Next, I just wanted to talk about detecting interaction on a logarithmic scale. So that's the scale that logistic regression is on, and that's not going up in even increments, that's going up logarithmically. So this table is laid out pretty similarly, where we have the individuals who are non-smokers and not exposed to asbestos, the just smokers, just asbestos, and joint effects. The only difference is because here our outcome is dichotomous, lung cancer or not. It would be for each row we would, to get the odds, we would say the number of cases that fit this description divided by the number of controls. And just for this referent no category, we have an odds of 1. And yeah, we would do that for each row. The number of people who are smokers not exposed to asbestos who had lung cancer, and those who didn't, 10 divided by 5, we get an odds of 2. If we continue down the table, we can get the odds ratios for each, dividing the odds of that by the odds of the referent. And this is a scenario where what we're doing is actually easier for logistic regression than linear regression, and that's not usually the case, where to find the expected joint effects, you would just multiply the odds ratio of the individual effects. So you can see here that the odds of having lung cancer if you're a smoker is 2 times higher, and if you're exposed to asbestos, it's 3 times higher. So we'd expect the joint effects of smokers who are exposed to asbestos to be 6, 2 times 3. If we were to find something larger than that, something like 10, that would be an example of synergism, where the joint effects of smoking and asbestos are greater than the product of their parts. Or antagonism, where the product of the effect of smoking and asbestos is less than if their individual parts are multiplied. And yeah, smoking and asbestos is a classic example of interaction. Just quickly, basically, like it is synergistic. These numbers aren't real, but when you're exposed to asbestos, asbestos gets carried into your airways on debris that you breathe in, and a main protective mechanism against the impact of asbestos, because when asbestos gets to the alveoli, it can cause cancer. A major protective mechanism against that is the cilia in the airways that are able to stop and collect that asbestos-containing debris and pull it up and allow you to cough it out. But if you're a smoker, then those cilia become paralyzed, and all of a sudden more asbestos is able to make it to the alveoli, which means for a given amount of ingested exposure, there is a much higher risk of lung cancer. So the odds of lung cancer with asbestos exposure becomes larger in the presence of smoking compared to the absence of smoking.